Okay, welcome everybody for the second talk in this session. We have Jose Morales here to speak about MLForecast, scalable machine learning based time series forecasting. I'm personally excited about this talk, and so if you all have any questions during the talk, use the Q&A functionality inside of Zoom or the chat, and then we'll save it for the end. So Jose, you'll have about 25 minutes. I know we're starting a couple minutes late, so I'll account for that, and then we'll try to leave some 5 minutes for Q&A at the end. Take it away.
Great, thank you. Um, so hi everyone, thank you for tuning in. Today I'm going to talk to you about MLForecast, which is a framework to perform scalable machine learning-based time series forecasting. My name is Jose Morales. I'm a data scientist at Mixla, where we do a lot of time series forecasting. So here's the outline. I'm going to start with some background and motivation to use this. Then I'm going to talk about some pain points in using machine learning models in forecasting. Then I'm going to talk about MLForecast's goal. Then since we are in the Dask Distributed Summit, I'm going to talk about scaling. Then I'm going to present two small examples and then some resources. So as a background, forecasting using traditional methods like ARIMA and exponential smoothing was a standard for a long time. And this works very well if you have a few time series which aren't really correlated. So if you have like a single store, different products, those sales probably don't correlate much, and you probably can get a lot of information from modeling them together. So using a single model for each time series was like the standard for a long time. Then some deep learning architectures have been designed for forecasting tasks. And they work well, but they need a lot of data. So they do need a lot of time series which are correlated and long because they sample windows. And so you need to have like a long history. And machine learning models haven't been used much. I think the main reason is because it's not straightforward to use them. So both traditional methods and deep learning architectures are designed for the forecasting task, but machine learning models aren't meant to do forecasting. They can do it, but it's not like they are meant to do it. And there wasn't much evidence of their performance. So last year, the M5 competition was held, which is the latest of the M competitions. This competition's goal is to incentivize research in forecasting methods and improve over existing benchmarks. So in each competition, some like new models arise. For example, in the M4 competition, I think it was the first one that used deep learning models. And there were some very interesting architectures where you, for example, one of the solutions was using like a mix of exponential smoothing with a recurrent neural network. So they are always very interesting. And the M5 competition in particular showed some very interesting results, mainly that machine learning models can outperform both the traditional methods and the deep learning models. And the M5 competition was actually split in two competitions. One was forecasting accuracy, which focuses on point forecasts. So you have to predict the sales as accurately as possible. And there was another competition where you have to measure uncertainty. So you have to forecast the quantiles of the distribution. And LightGBM specifically was used in both, in the winning solutions for both competitions. So that was very interesting to see that machine learning models are good at both tasks. So the pain points in using machine learning models for forecasting, I think the first one is the preprocessing. So if you have a lot of time series, you have to compute the features for training. And that is embarrassingly parallel because you can do split by the series or compute the features independently. But doing it efficiently is hard. So if you use pandas, you can group by the series ID and then use the transform method to compute some transformation. But that can take a very long time because the way pandas does it is you split the data frame by groups, apply the transformation, and then concatenate it back. So since we're always using the same groups, which are the time series in this case, we could maybe have a better data structure. And we can compute each feature independently. So say we have our time series stored, each feature doesn't depend on the others. So this is a good use case for multi-threading. So the MLForecast approach is that all the time series are stored in a grouped array, which is composed of two 1D arrays. One is the first array stores the series values in a 1D array called data. And the other one stores the group boundaries in another 1D array called the pointer. So if you have used SciPy sparse matrices, this may look very familiar to you. SciPy sparse matrices use these structures as well as another 1D array with the indices. But since we only care about where a series starts and where it ends, we just need these two arrays. And this allows for fast iteration and updates. I'm going to talk about the updates in a minute, but iterating this array is very fast. So if you can think about it, the in pointer has the start and the end. So you can take, for example, the boundary start and end and use that to slice data. And since these are NumPy arrays, this is very fast. And the transformations are defined as non-budgeted functions. So if you have used Numba before, Numba has a decorator, which at runtime compiles your function for the types of the inputs. So the first time that you run the function, it is compiled, so it takes a bit of time, but subsequent calls to that function are extremely fast. And they actually have an argument in the decorator that allows you to bypass the GIL. So you can actually do multi-threading with CPU-bound tasks like these ones. The second pain point is the updates. So using lag-based features requires that you update them in each time step. So each time you want to predict the next time step, you have to update all your features with the latest values of the time series. And once you have that prediction, you have to plug it back in the series values so you can recompute the features again and so on. So the MLForecast approach is that you recompute the transformations and keep only the last value. This is like this is doing a lot of work, more work than it needs. But I found that actually it is faster to do this, to recompute the whole transformation using this non-budgeted function than using like a formula to update. So for example, if you have the expanding mean, you need to add the next value, add 1 to your samples and just divide it. But you doing that like takes a lot of time because it's just Python code. So using, I found that using non-budgeted functions actually work better. And you can use multi-threading, which is like the main advantage, I think, with using Numba. And you have to update the grouped array with the predictions. So since these grouped array are just two 1D arrays, this is very fast as well because you just copy the two arrays and just like insert the values and increase the sizes of the groups. Here's an example to describe these pain points. So say we have this time series, we have 3 time indices. These Y column are our series values. So for the first time index, we don't have a lag 1. For the time index 1, we have the lag 1 is 10, which is the value in the previous time. And then in time index 2, we have the lag 1 is 11, which is the value in time index 1. So say we train a model using this feature. So we train a model to predict the series values based on the lag 1. So how can we predict the time index 3? So say we are now in time index 3. We need to have our lag 1 in order to predict the next value. So what we do is, since we are in time index 3, the lag 1 is the value in time index 2. So we just move this value here. And now that we have all of our features, we can compute the predictions as a model applied to this feature. And what about time index 4? So now we need the value of the series in time index 3. Since we don't have the real value, what we can do is we can take this prediction and plug it in here as if it was the value of the time series. And now that we have this value here, we can compute the predictions as our model applied to this feature. And this goes on for as many time steps as you want. Of course, if you are using a lag that is further away, you can actually plug in real values until you run out of them. So the goal of MLForecast is to provide a high-level API to use machine learning in forecasting tasks. So it abstracts away most of these details. So you just have to provide the data, a flow configuration, which is where you define the features that you want to use. These include lags, lag-based transformations, and data attributes. And this also has other configurations like whether or not to drop nodes. So for example, in this case, this row will have, the lag 1 will be a node. So you can decide whether or not you want to keep them. You can decide whether or not to use multi-threading and what are the static features. And the third input is a model. There are two modes in ML forecast. There is a local mode, which you can think of as scikit-learn, which is a single machine, single process. So if you are using that mode, you can use any scikit-learn compatible regressor. And for distributed training, you can use either LightGBM or XGBoost. This is because in order to perform distributed training, we need to have models that implement distributed training through a Dask interface. So if you saw James' talk, LightGBM recently incorporated distributed training through Dask, and XGBoost has had it like maybe for over a year. So this project just uses those implementations to do distributed training. So the forecasting steps are the input, where you define your data, your flow configuration, and the model. Then the preprocessing step, which computes the features to build the training set. Then you do the training step, which just feeds a model to this training set. And then comes the forecasting, where all the steps that I described in the example are performed. So you update your features using the latest values of the time series. Then you use those features to predict the next time step. And then that prediction gets plugged into the series values, and then you repeat until you have enough predictions. And now the scaling part. So if you notice, most of the steps are independent between series. So if you want to perform distributed training, you can split your data by series. So say this chunk has 10 series and this other one has another 10 series. You can load them independently. You can perform the preprocessing independently. This is considering that you are only using lag-based features. So this is independently for each time series. And then the training part, this part actually requires communication because it trains a single model with all the data in a distributed way. So this line here represents that there is actually some communication going on here. And once the training is done, the training model is sent to every worker, and you perform the updates and predicts independently in each partition. So there is no communication here. So this avoids data movement, and the only step that requires communication is the training part. So this scales very well. And now I have some examples. So the first example is how to set up your data to use MLForecast. There's a CLI interface. So if you don't want to have a script or something like that, so you just want to create a quick baseline or are more comfortable with configuration files, you can just get away with saving your data in the required format and call the CLI. So the required format is this. You need to have an index with a unique ID. This identifies each time series. Then you have a date stamp column with the dates, a Y column with the values, and all the other features are considered static by default, unless you specify in the flow configuration that only a subset of them are actually static. So the static features are repeated in every time step. We can take a quick look at the data. So this is daily data with a high seasonal pattern in the day of the week. So this is very easy data set. It's just for demonstrating purposes. So what we do is we split our data in partitions. So here we have 2 partitions, and then we save it to this directory, data train. And then we have this configuration file. Here we are saying where is the data. So the data is in prefix input. So it will look in data train. It will write the outputs to prefix output. So in this case, data outputs. And you specify the format. So this is in Parquet format. The current formats available are just CSV and Parquet. Then here's the flow configuration. So the features, our series have daily frequency. We want to use lag 7 and lag 28 as features. And the lag transformations are defined like this, where it's like a dictionary where the key is the lag and the values are the transformations. So in this case, we are saying we want to compute the expanding mean over the lag 1. And over the lag 7, we want the rolling mean with a window size of 7 and the rolling mean over a window of size 14. We want the week, month, and year as features. And we want to use to perform these transformations using 4 threads. Then the forecasting horizon is 56, so 8 weeks. And then this part, we are specifying that we want to perform distributed training. So here we are saying the model this can only be LGBM forecast or XGB forecast. And these are the parameters. So these are passed to the constructor. And then we are specifying here what kind of cluster we want. So this can be any kind of cluster you want. This can be a Kubernetes cluster, like a Fargate, whatever. And here you specify the keyword arguments, which are passed to the constructor as well. So here we are going to use a local cluster for demonstration with 2 workers, 4 threads, and 6 gigabytes of RAM each. So once you have this configuration set up, you just call the binary. We just call MLForecast. We can do help. So here we are saying, we see that we use this as MLForecast and pass the name of the configuration file. So we just say MLForecast distributed YAML. Let me see if this is connected. Not sure. Okay. So here we can see the task graph. Here we see that the data reading is being parallel as well as the preprocessing. So this is loading the partition and performing the preprocessing independently. Now the preprocessing is done. Now it's doing the training. So as James said, Dask doesn't know that there is actually some communication going on here. So this is LightGBM's C++ network interface doing the distributed training. So we can see that it's using multi-threading. And once the training is done, the model will be sent to each worker and the forecasting step. So here we can see this is the booster. It is sent to each worker and each worker performs the predictions independently. Okay, that's done. So now our outputs are saved to data outputs. Now there is a forecast folder, and within that folder, there are the partition results. So these partitions correspond to the training partitions. They contain the same series IDs, only that these contain the predictions instead of the training set. And now, yeah, I forgot to start off because. So I'm going to do a more scalable example, I guess. So this was running on a local cluster with only 2 workers, but you can scale this out to a lot of data and a lot of workers. So here I'm starting a cluster with 16 workers. Each worker has 4 threads and 16 gigabytes of RAM. You can actually use this software if you want. This is a coiled cluster. So if you use this software environment, you can run this experiment yourself. I should have started this cluster when I started in the previous example. So this is going to take a minute, but maybe I can describe the next steps. So I'm going to generate some random series. These are going to be daily series as well as in the previous example with only daily seasonality. So I'm going to create a 1,000,000 time series and spread them across the workers. So here I have 16 workers, so I'm going to have 1,000,000 divided by 16 series in each worker. And then I'm going to perform distributed training using all of these time series. I'm going to train a very small model. So as you scale to bigger, to large volumes of data, you will see that the training part becomes the most expensive part. So that's expected. So what I recommend is using as few workers as you can with as many threads as you can, because both LightGBM and XGBoost use multi-threading within each machine. So if you can have 4 machines with 4 threads, that's better than having 8 machines with 2 threads. So always go for for the highest number of threads that you can. And actually the MLForecast, here I'm specifying that I want 4 threads for the preprocessing and updates. So this will try to use the CPU resources as efficiently as possible. Okay, so now we have our cluster set up. So I'm going to generate the series within each worker. This can take like 20 seconds maybe. So I can talk about the flow configuration in the meantime. So this is exactly the same as the YAML. here I'm specifying that I have daily series. I want lag 7 and lag 28 as features. And in this case, I'm only using the lag 7 for transformations. So I'm computing the rolling mean over a window of size 7 on this lag 7, and a rolling mean over a window of size 14. Day of week, month, and year as date features. And I think that's done. So let's see, we have 500 million rows. And just to check that we have exactly the number of series that we want. So we have a million time series. So here we define the flow configuration. We define the model. As I said, this is a small model for demonstration purposes. If in real use cases, you would have like very deep trees and a lot of them. So I have a notebook in the M5 competition using distributed training. So I'll post the link after this. So that's like a more real world example of using this distributed training for a real data set. So we can see that it's performing the preprocessing now. It's preprocessing the 16 partitions. Okay, took about 20 seconds. And okay, yeah. Now it's going to start the training. I think that was, yeah, one partition was missing. So okay, now it's trained. So as you can see, this is what I mean by using as many threads as you can. So LightGBM will use multi-threading within each machine. So you can speed up the training by using many threads here. It's going to take like a minute. And once the model is trained, we will perform the same. So I think I didn't mention it. In order to perform the forecasting, you pass the model and the flow configuration, and you just call fit on your data. In this case, data is the Dask data frame here, with the same structure that I defined in the example. So the ID, the index is the unique ID. Here's the daystamp column and the Y column. Okay, now this finished training, so this took a minute 20 seconds. Now I'm going to predict. Once the forecast is trained, you just call predict with the horizon here. So I'm asking for 28 for the next 28 time steps. So this is, as you can see, is doing multi-threading, not as efficient as LightGBM, but it's at least it's using more than 100% CPU, so that's good. And you can see, maybe we can look at the graph. Okay, no graph. Okay, so that took 17 seconds. We can see these are the predictions. So these are the predictions for the ID0. Here are the dates and the predictions. And we can take a quick look. So we'll look at the last 50 values of the training set and all the predictions. So we can see this is a very easy data set, but you can see that it's capturing the pattern very well. Okay. For resources, if you're interested in this, check out the repo. If you have any feature request or like you want to make a contribution, you're welcome to do it. Here's the documentation. Here are two notebooks in Kaggle. So for the M5 competition in the forecasting accuracy, I found a solution that took a lot of time. So that was like part of the motivation to build this. Actually, I think the prediction step took like 2.5 hours, and using this notebook, it takes 6 minutes. So this, and you can see that it actually used multi-threading because the wall time is like, it's I'm not sure. I think the CPU time is 4 times the wall time. So you can you have 4 threads in the Kaggle kernels. So that's nice. And here's the distributed example. So both of these notebooks use MLForecast, only this uses a local interface, and this is trains on a remote cluster. And if you want to contact me, here's my email. And yeah, I think that's it.
Great. Well, thanks, Jose. We have a couple of minutes for questions, so feel free if anybody has questions, go ahead and add it in the Q&A section here on Zoom, or put it in the chat, and I'll kind of read them off. Looks like we've got one question now. The question is, does MLForecast support exogenous or dynamic features?
Yeah, sure. So let me go to this link. So the default flow just repeats the static features. But if you have like a different requirement, for example, in the M5 competition, they had the calendar and the prices. So when you computed the next time step, you had to do a join with the prices to get the price for that week and for that store an item. And you also had to know if it was a holiday, for example. So in this competition, in the public leaderboard, which is what this notebook solution is for, I think the second week is a holiday, so that impacts the model a lot. So what you have to do is define a custom predict function, which is this one. So when you call update features, you get the static features and the next values of the transformations. But if you want to add something else, you just, for example, I'm joining with the calendar here, I'm joining with the prices, I'm sorting the index because sometimes the merge like moves in row order, and then you just predict. And actually, this notebook specifically produced three predictions and then averaged them. So here we am. Here I am multiplying the predictions by some alpha, which is in the original notebook if you want to check it out. And yeah, so this actually uses those features and updates them in each time step. So here it is the code. You just, in the predict method, you just pass the predict function, and that's it. And as you can see, it took 6 minutes here.
Great. We do have just one more minute for any final questions. I'll give everybody just a second to throw it in. Otherwise, I have more of a just like generic or philosophical maybe question than specific to the library. Okay. I mean, so my question would be like, you know, there's a lot of other like, you know, there's time series forecasts like libraries that might use kind of, you know, maybe other tools like deep learning or other kind of technologies. Where do you see like kind of, and in a lot of machine learning applications, like gradient boosted tree models can perform better than deep learning. Do you have you kind of seen any of that, you know, either with this library or other ones, you know, in cases where it'd be preferable to kind of do gradient boosted trees versus kind of deep learning based forecasts?
Yeah, I think it depends on the series length. I think deep learning models are very good when you have long series, but this, for example, using LightGBM, I was able to get a better score than using deep learning models for series that weren't very long. So I had weekly series with lengths like from 10 to 50, which are you don't even span a year, so holidays and stuff like don't get captured. But LightGBM performed very well, specifically because you can have different objectives. So I think I used the Tweety. I had the distribution was very skewed towards 0. So using different objective functions as well can help a lot. And yeah, so this is like to give people a different tool in their repertoire. So yeah, you can definitely try as well. In Mixlab, there's another team working on deep learning approaches. So you can definitely check it out once it's open source.
Yeah, definitely makes sense. And it's really nice when you can already use like models that can take advantage of Dask and kind of scaling out. You know, can sometimes be more challenging with other algorithms. So, well, thank you again, Jose. We're going to swap it over to our next speaker, but everybody stick around.